Next chapter that we are going to discuss is kinetics. Now, the only thing that kinetics really is just how fast a reaction will occur, or the reaction rate. So, some factors that can affect the reaction rate. Physical states of the reactants. Let's say, we got a solid and it's really compact. It'll take a long time for it to react. Kind of think of a sugar cube inside water. If we put a sugar cube in water, it's going to take a long time for it to dissolve compared to granulated sugar. Not powdered sugar, but sugar that's in kind of more powder and kind of looks like sand. That will go a lot faster because it has a larger surface area. Another one, reactant concentration. So higher concentration, more likely for it to speed along than a reactant that has a lower concentration. Temperature. Think about thermochemistry. Higher the temperature, things are going to be moving around a whole lot more, and they're going to come into contact with one another, and they're actually going to do something. And our last thing, catalyst. So we've talked about catalyst before. Speeds up a reaction. Okay, it helps the reaction go along, but it's not part of the reaction. It's just there to help it. So if we were looking at a reaction, let's just go with this really generic formula, A to B. A being our reactants, B being our products. We can say that the rate of appearance of B, because, just like what we were dealing with equilibrium, do we really have any products at the beginning of the reaction? No, so they are appearing. So the way that we can find the rate of appearance is we can take the change in concentration of B over the change in time. Now, since B is appearing, that's telling us that A is disappearing. So the rate of disappearance of our reactants, we're going to put a negative sign out in front of the change in concentration over the change in time. Okay? Now, if we're looking at a reaction, an actual balanced reaction rates and stoichiometry. This is really easy to do. So we know that the rate of our reactants is disappearing and the rate of our products are appearing. So negative sign out in front of the reactants, positive sign out in front of the products. If we have any coefficients in front of our reactants or our products, we're going to take that coefficient and we're going to put 1 over that number. So in this case, 2HI yields to H2 plus I2. So the rate is equal to negative 1/2 times the concentration, the change in concentration of HI over change in time. And this would be equal to the change in hydrogen's concentration over change in time, which is equal to the concentration of I2 over T2. Now, why are they all equal to one another? Well, since they're all in the same reaction, and that's what's going to happen. So let's kind of look at an example of this. It says, how is the rate of which ozone disappears relate to the rate at which oxygen appears in the following reaction? Okay, so here's our reaction. 2O3 yields to 3O2. If the rate at which O2 appears, change in O2 over change time, is equal to 6.0 times 10 to the negative fifth molar per second at a particular instant, at which rate is O3 disappearing at the same time. Okay, so let's kind of look at this one. So we said 2O3 gas yields to 3O2 gas. So that means that the rate is equal to negative 1/2. Let me start all over. Negative 1/2 change in O3 over change in time is equal to 1/3 change in concentration of O2 over change in time. So we want the rate of ozone disappearing. So we want the negative change in concentration of O3 over change in time by itself. So we're going to multiply both sides by 2 so we can get rid of that 1/2. So negative change in O3 change in time is equal to 2/3 times concentration of O2 over change in time. Now, if we look back over here, we were given the rate of appearance of O2 as 6.0 times 10 to the -5 molars per second. So we're going to put that into our formula right here. So 2/3 times 6.0 times 10 to the -5 molar per second. And let's see what that comes out to be. Two-thirds times 6.0 times 10 to the -5. And we'll put it in scientific notation since it was already in scientific notation. So that comes out to be 4.0 times 10 to the -5 molar per second. Now, the next part is, figuring out what is the rate law for a particular reaction. Okay, and when we're trying to figure out the rate law, we're trying to figure out what order each of the reactants are in. Now, the order is just what power is the concentration raised to. And we can't just look at a reaction and say, oh, that's going to be in first order or second order, if it's to the first power to the second power, and so on and so forth. We have to figure it out with experimental data. So we're going to look at that with this example right here. So our two reactants that we have ammonium and we have nitrite. And we have also the observed initial rates. So we have the initial concentrations. Now, the way that we figure out what order each one is in, we're going to take two experimentations in which the concentration changes for the reactant we're looking at, but it stayed the same for the other one. So in the case if we want to figure out what order is ammonium, okay? Like I said, is it first order? Is it just raised to the first power? Is it raised to the second power? So on and so forth. We're going to use two experiments where the concentration for ammonium changes and the concentration of nitrite does not change. So if we look at experiment 1 and 2, ammonium's concentration changes, nitrate's doesn't. We're also going to use this observed initial rate. So the way that we find it is we're going to take the ratio of experiment 2 over experiment 1, x, figure out its power, and that's going to be equal to our ratios of our observed initial rates. So times 10.8 times 10 to the -7th molars per second over 5.4 times 10 to the -7 molar per second. All right, so let's put our numbers in here. So 0.0200 over 0.0100 molar. That's to the x power, finding x. 10.8 times 10 to the -7th molar per second over 5.4 times 10 to the -7th molar per second. Now, hopefully you can kind of see what's going to happen here. This is going to be 2 over 1, so 2x is equal to, then since both of them are times 10 to the -7th, we don't really have to worry about that. So 10.8 divided by 5.4 comes out to be 2. 2 to what power will give us 2? 1. All right, so ammonium, it is to the first order, or to the first power. Now let's do the same thing for nitrite. Let's pick two reactions where the concentration changes for nitrite, but stays the same for ammonium. So we can let's use 4 and 5. Okay. All right, so what order is in O2? And let's say we're going to use 4 and 5. So 0.0404 molar over 0.0202 molar. And I'll just use Y since it's a different reactant. And that's going to be equal to 21.6 times 10 to the negative 7th over 10.8 times 10 to the negative 7th, and that's molars per second. So that's the change, the observed initial rate, that's the change in concentration over time. Okie dokie, so 0.0404 divided by 0.0202. Now 21.6 divided by 10.8. That's going to turn into 2 as well. So once again, y is equal to 1. So both of our reactants in this reaction are to the first order. So the way that we write this rate law, rate is equal to K. K is the rate constant, okay, times concentration of ammonium. Now, since it's raised to the first power, we don't really have to put a 1 with it. Now, if it was raised to the second power, third power, so on and so forth, we would have to put 2, 3, 4, whatever, times concentration of nitrite to the first power. Now, we can actually calculate out the rate constant with this information. After we figure out what order our reactants are in, to figure out the rate constant, we're going to plug in information or data from one of our experiments into our formula down here. Okay, so the rate, we can use one of the observed rates. So let's just use experiment 1. All right, so the observed rate, the observed initial rate, so rate 5.4 times 10 to the negative 7th molars per second is equal to K times, and then we're going to put the initial concentrations in from experiment 1 into our formula down here. So 0.0100 molar times, 0.200 molar. We just need to solve for K. So K is going to be equal to 5.4 times 10 to the negative 7th molars per second all over 0.0100 molar times 0.200 molar. Okay, so let's get our calculator out. 5.4 times 10 to the negative 7th divided by 0.01 times 0.2. Sorry, trying to get this to show up. And so our rate constant, wait a minute, it did not, let's do it again. 5.4 times 10 to the negative 7th divided by 0.01 times 0.2. There we go. Yeah, that looks a lot better. 2.7 times 10 to the negative 4th. Now the units that's going to go with it, we have molar per second all over molar squared. So our rate constant, K, is going to be per molar per second. Okay. Now, let's say we're trying to find the concentration or the change in concentration over time. So in this case, we're going to be told whether a reaction is going to be in a first order reaction, a second order reaction, a zero order reaction, or it could be a half-life situation. All right, so if it's a first order reaction, the rate is equal to our disappearance of our reactant over change in time, which is equal to our rate constant times the concentration. Now the formula that we really use for a first order reaction is this. Natural log of our concentration at a certain time is equal to negative rate constant times time plus the natural log of the initial concentration. So let's look at an example of using first order. So it says the decomposition of a certain insecticide in water at 12 degrees Celsius follows first order kinetics with a rate constant of 1.45 per year. The initial concentration was found to be 5.0 times 10 to the negative 7 grams per cubic centimeter. What will the concentration be 1 year later? How long will it take for the insecticide concentration to decrease to 3.0 times 10 to the negative 7 grams per cubic centimeter? So two questions in this one. Let's first figure out the first one. What will the concentration be 1 year later? Okay, so natural log of our insecticide 1 year is equal to, now it gave us a rate constant as 1.45 per year times 1 year plus natural log of our initial concentration, which was 5.0 times 10 to the negative 7th grams per cubic centimeter. So let's kind of put this part in first into our calculator. So negative 1.45 times 1, negative 1.45 plus then the natural log of our initial concentration, which was 5.0 times 10 to the negative 7th grams per cubic centimeter. So that's coming out to be, I'll put this right back in the regular, negative 15.96 grams per cubic centimeter. Now, we're trying to find the concentration after 1 year, and it's the natural log. So we need to get rid of that natural log. So we're going to, if we look at the natural log, let me zoom, get this in, right above it, this button right here, we have e to the x. So we're going to take e to both sides. So if we do that, we come up with the concentration of the insecticide after 1 year is equal to e to the negative 15.96 grams per cubic centimeter. Okay, so let's take e to the negative 15.96. Our concentration comes out to be 1.17 times 10 to the negative 7th grams per cubic centimeters. All right, now, second one. How long will it take for the insecticide concentration to decrease to 3.0 times 10 to the negative 7 grams per cubic centimeter? All right, so that is our concentration that we put over here because it's at a certain time. So natural log of 3.0 times 10 to the negative 7th grams per cubic centimeter. That's equal to, now K, once again, that was given to us. That's that 1.45 per year times time, that's our unknown variable, plus natural log 5.0 times 10 to the negative 7th grams per cubic centimeter. Okay, so let's kind of get the natural logs to both sides. So I'm going to take natural log of 3.0 times 10 to the negative 7th minus natural log of 5.0 times 10 to the negative 7th. Okay, I'm coming up with negative 5.11 times 10 to the negative 1st. And actually, units don't really matter in this situation. That's equal to negative 1.45 per year time, because the grams per cubic centimeter gets canceled out in this situation. So we need to get T by itself. So we're going to take the negative divide both sides by the negative 1.45 per year. So negative 5.11 times 10 to the negative first divided by negative 1.45. And come up with 0.35 years. Okay. Now, the other formulas that we can have, like I said, if it's a second order reaction, rate is equal to, our rate of disappearance is equal to K times the concentration of our reactant squared, second order, raised to the second power. Now, the formula that we use is we take the inverse of the concentration at a certain time, and that's equal to rate constant times time plus the inverse of our initial concentration. Zero order rate of our disappearance is just equal to K. So you kind of look at it, first order we said that the rate is equal to K times concentration of A. Second order rate is equal to K times the concentration squared. Now zero order means that the concentration would be raised to the zero power. Well, if it's raised to the zero power, that just means that it's going to be 1. So that's why the rate is just equal to K. Now the formula that we use is the concentration at a certain time is equal to negative K times T plus the initial concentration. Half-life, I'll let you look at this, but what it boils down to is half-life is equal to 0.693 over R constant. Okay, so let's do one problem more for this part, then I am going to stop for this video and have you work on some problems dealing with this stuff right now, and I will make a second video over the second part of the chapter. Alright, so this problem that we're going to look on says the following data were obtained for a gas phase decomposition of nitrogen dioxide at 300 degrees Celsius. Here's our reaction. Nitrogen dioxide breaks down into nitrogen monoxide 1/2 O2. Is the reaction first order or second order? And as we see over time, the concentration of nitrogen dioxide does start to decrease, as it should. So now, figuring out whether it's first order or second order, this is where we have to graph. Now, in first order, we have natural log of the concentration. And if we look at the second order formula again, second order, we have the inverse. Okay, so what we're going to do is we're going to figure out what the natural log is for each concentration, and we're going to figure out what the inverse is. And we're going to just make a table at first. So time, natural log of the concentration, inverse of the concentration. Okay, time still stays the same, 0, 50, 100, 200, 300. Alright, so natural log of 0.0100, negative 4.61, natural log of 0.00787, negative 4.84, natural log of 0.00649, negative 5.04, 200, so natural log of 0.00481, negative 5.34, and for 300, natural log of 0.00380, negative 5.57. All right, now the inverse. Okay, 0.100 inverse 100. 0.00787 inverse 127. 0.00649 inverse 154. 0.00481 inverse 208. And 0.00380 inverse 263. And I'm not really concerned about the units right now. Now, after we've done that, the next thing is we're going to have to graph it and see what our two graphs look like. The x-axis is going to be the time, which is given to us in seconds. And for the first order, y-axis is going to be the natural log of the concentration. Okay, so we have 0, 50, 100, 200, and 300. And actually what I should have done, since all the natural logs is negative, I'm going to have them going down this way instead of going up. That's my fault. Alright, so let's kind of negative 4, negative 4.1, negative 4.2, negative 4.3, negative 4.4, negative 4.5. Let's just kind of start there. Maybe I should have started up 4.6, 7, 8, 9, negative 5, 5.1, negative 5.2, negative 5.3. Okay. So at 0 times 0, we have negative 4.61. Then at 50, negative 4.84. 100, negative 5.04. 200, negative 5.3. And at 300. Okay. So if we look, it's kind of curving downward. Not the greatest graph. Apologize for that. Now, kind of save some time and paper. Now on the positive y-axis, this is where I'm going to have the second order information. So I'm going to have the inverse of the concentration. $100, let's say 120, 130, 140, 150, 160. Kind of go from there. So at 0, we said we had 100. At 50, 127. 100, 154. Okay, now this one, I know I'm just doing it freehand, it kind of sucks, but you notice how we get a nice straight line. So whichever order gives us a nice straight line instead of a curve, that's telling us what order this is in. So this one, since the second order information gave us a straight line, the reaction is second order. Okay, so I'm going to stop the video right here. Hopefully, take notes. If you have questions, please email me. Let me know. I'll help you out as much as I can, and I'll give you an assignment over this part. Work on it. I'll send out the key so you can check your work and everything. And then I will have a second video over this next part of the chapter. So if any questions, please let me know. Thanks for watching.